Hello, I'm Silvia Vicente from the University of Lisbon. In this poster, I summarize our observational and modeling results on the structure and properties of photodissociation regions in proplyds. Externally illuminated protoplanetary disks, also called proplyds, are found in many regions of massive star formation, but they were first discovered in the Orion Nebula cluster near the trapezium stars, identified by their typical teardrop-shaped ionized cocoons with embedded disks seen in extinction in HST images. Several of these disks have been also spatially resolved in the forbidden lines of optical oxygen and raw vibrational H2, both with HST and from the ground with adaptive optics. Recently, they were also resolved in HCO+ and CO with ALMA. So, check the posters by Carlo Manara and Riot Boyden. Proplyd morphology and the observed gas emission from the disk have been successfully interpreted with a photon dissociation region or PDR model. In this model, the soft FUV radiation from the massive stars reaches the disk surface, where it dissociates molecules, ionized carbon, and heats the gas, creating a highly structured and layered PDR. The FUV radiation can also induce a slow atomic wind from the disk surface at radii where the thermal velocity of the gas becomes larger than the escape velocity. But the structure of proplyd PDRs can differ from classic PDRs, and that is simply because the properties of the dust and gas in the disk are likely different from those of FUV illuminated molecular clouds or the diffuse interstellar medium. The main gas heating mechanism in classic PDRs is the photoelectric effect on small dust grains and polycyclic aromatic hydrocarbon molecules, also known as pHs. However, in our work published in 2013, we found that pHs in the proplyd HST10 are underabundant by a factor of 50 or more relative to the diffuse ISM. And this reduced significantly the photoelectric heating at the disk surface. So, we need to ask what are the key mechanisms driving the heating and cooling of the gas, and therefore the photoevaporation of the disk. Bernet and Vicente conducted the first and unique far-infrared survey of proplyds with the Herschel Space Observatory. 2 proplyds in the Orion Nebula cluster and 1 in the Carina Nebula were observed with their PHI and PAX instruments. The goal was to detect far-infrared lines of atomic oxygen, ionized carbon, and high J CO, which are main coolant species in classic PDRs. The data was analyzed by Jason Champion as part of his PhD thesis and published in a paper, which also includes the non-spatially resolved detection of HCO+ in a silhouette disk. This was obtained with ALMA in Cycle 1, Observations of the Orion Bar by Javier Gocoechea. Regarding Herschel observational results, we see that the proplyds in Orion were strongly affected by nebula contamination and beam dilution of the proplyd signal. Nevertheless, we were more successful with the Carina proplyd because of its larger size and the fainter background nebula emission. The Herschel data was then combined with archive observations and analyzed with a 1D PDR model based on the Meudon code. This model reproduced most of the observations and provided the physical conditions, that is, the temperature and the density at the surface of the disk. The model also shows that the gas thermal balance results from a complex combination of several heating and cooling mechanisms, and therefore cannot be interpreted only on basis of the classic solution, where the photoelectric effect dominates the heating and far-infrared line emission dominates the cooling, but please check the paper for further details. The James Webb Space Telescope will be the pristine instrument to study the warm gas and dust in PDR regions at all scales and in different environments, from distant galaxies to protoplanetary disks. The co-Is in this work are part of the core team of an approved James Webb early release science project to study one PDR region in detail using James Webb instruments. The data will be immediately available after observations, as well as customized PDR analysis tools, which will be developed by our team. So stay tuned and check the website for more information. Thank you.